Hey everyone, and welcome to this explainer. Today, we're doing something pretty exciting. We are decoding the foundational rules of matter. Whether you're a fresh student gearing up for those DP 803 or Class 11 exams, or you just really want to understand the literal building blocks of the universe from the ground up, you are in the exact right place. We're going to take these abstract chemical concepts and turn them into a practical, everyday toolkit for you. So, think about the ice in your glass. What are the actual fundamental rules that govern that matter? And how on earth do we measure things that are completely invisible to the naked eye? Well, chemistry isn't just about randomly mixing colorful liquids in beakers, right? It's the ultimate science of characterization, change, and measurement. It tells us exactly what things are made of, how they behave, and how we can quantify them. To answer those big questions, here is our roadmap for today. First, we'll cover the building blocks of matter. Second, states and phase changes. Third, we'll review laboratory separation techniques. And finally, we'll wrap up with the language of measurement.
All right, Section 1, the building blocks of matter. We are establishing a baseline vocabulary for the universe.
We literally have to start at the bottom, right? The atom. Now, we always hear that atoms are small, but what's truly mind-boggling here is the sheer scale. An atom is about 0.2 nanometers. To put that into perspective, that is so unimaginably tiny that just a single pen dot, like a full stop at the end of a sentence, contains roughly 2 million atoms. It is the absolute smallest particle of an element that can actually take part in a chemical reaction. Building on that, when atoms join together, they form a molecule. A molecule is the smallest piece of a pure substance that can stand entirely on its own, independently, while still keeping all its chemical properties. Now, while some atoms, like the noble gases, are perfectly happy existing by themselves, most actually need to bond together to form molecules just to achieve stability. And the number of atoms in that molecule? That's what we call its atomicity. Moving right along to Section 2, states and phase changes. Let's see how temperature and internal energy transform matter. Picture a solid block of ice again. The particles inside are locked into a fixed position, just vibrating in place. But when you add heat, you increase their internal kinetic energy. They start vibrating faster and faster until, at a very specific temperature, that motion actually overcomes the cohesive forces holding them together. The rigid structure collapses, and boom, the solid turns into a liquid. And here's a cool fact. During this exact melting phase, the temperature actually stays constant because all that added heat is busy breaking those forces of attraction. Now, once we have a liquid, we can turn it into a gas. Okay, listen up because this is a classic exam trap. You absolutely need to know the critical distinction between evaporation and boiling. Evaporation is a quiet, steady, surface phenomenon. Molecules right at the top escape into the air, and this happens at literally any temperature, which, by the way, is exactly why evaporation causes cooling. Boiling, on the other hand, is a highly energetic phase change happening throughout the whole liquid. It creates bubbles everywhere, it only happens at a specific temperature when the vapor pressure matches the atmospheric pressure, and it absolutely does not result in cooling. But you know what? Sometimes matter just completely breaks the rules and skips a step. We call this sublimation. It's a fascinating shortcut where a solid, when heated, vaporizes instantly into a gas, totally bypassing the liquid phase. You've probably actually seen this in the real world with solid air fresheners or dry ice. Let's step into the lab for Section 3, laboratory separation techniques, isolating components from a mixture. So let's talk filtration. The crucial point of a proper setup isn't just randomly pouring a muddy liquid through some paper. It actually comes down to 3 precise procedural steps that are practically guaranteed to pop up on your practical exams. Number 1, use a fluted filter paper. This increases the surface area to accelerate the process. Number 2, you gotta keep the stem of the funnel continuously full of liquid to create a gentle suction effect. And 3, ensure the tip of the stem touches the side of the receiving beaker. This completely avoids splashing and losing your carefully separated liquid. When you actually build this physical assembly on a lab bench, you'll see the funnel, the filter paper snugly inside it, and the beaker right below. This exact setup is your go-to primary tool for separating insoluble solid particles out of a liquid. Ultimately, these physical lab techniques serve a much greater purpose in analytical chemistry. Analytical chemistry is all about characterization, and it really relies on 2 main pillars. First, qualitative analysis. That simply answers the question, what exactly is in this substance? It's all about detecting the elements. The second is quantitative analysis, which answers exactly how much of it is there. It determines the relative amounts. A perfect example of this analytical power is chromatography. It's a method we use to separate the components of a mixture based on how they travel across a surface. We identify these components based on their specific retardation factor, or RF value. The math here is actually super straightforward. You take the distance traveled by the specific component, and you divide it by the total distance traveled by the solvent. It's a really simple but incredibly powerful equation to detect the purity of a substance. And finally, Section 4, the language of measurement, quantifying the physical world using SI units. To speak this scientific language, you absolutely need the foundational SI system, the International System of Units. I highly recommend taking a mental snapshot of these exact base units, because they are literally the grammar of quantitative chemistry. We measure length in meters, mass in kilograms, time in seconds, temperature in Kelvin, and the amount of substance in moles. That mole is especially vital for us. It represents a specific, massive number of atoms or molecules, which allows us to translate the invisible, microscopic world into measurable quantities in the lab. And then, from those basic building blocks, we derive more complex units. By combining them, we get the joule for measuring energy, the Newton for force, the Pascal for pressure, and the Coulomb for electrical charge. These derived units are exactly what allow us to mathematically describe absolutely any chemical phenomenon we observe. So think about how far we've come in just a few minutes. You now have the fundamental chemist's toolkit right at your disposal. You know how to define microscopic atoms and molecules, you totally understand the kinetic energy driving phase changes, you know exactly how to execute laboratory separation techniques, and you speak the universal SI language of measurement. So the only question left for you is, how will you apply these rules to decode the universe around you? Thanks for joining me on this explainer, and keep exploring.